Thanks for inviting me here. So I just want to get started, and I'll tell you a little bit about the disturbance mapping process we use at ARROS to keep the LANDFIRE data sets up to date. In order to perform LANDFIRE's mission, we need to have an up-to-date database data set reflecting changes in management activities and natural disturbances. So, and in order to provide the best data set, should be, capture both the time of disturbance and the spatial extent of and severity related to that landscape change. So we've developed, a system has been developed to capture that information. So I'll walk you through that product just a little bit. So our disturbance product, as you've heard alluded to earlier today, it's an annual product. So for LANDFIRE 2010, there are really three products. One for 2008 that represents 2007, 2008 change. 2009, which is 8 to 9, and then 9 to 10 change. And the legend's kind of fairly sizable. There's 160 codes that we're mapping to, so 19 different disturbance causes. Most of those come from the events database that Brenda's talked about earlier, and that we'll talk about a little bit more. And then we have different confidences based upon the convergence of information and evidence, and we'll delve into that a little bit as well. So the disturbance sources that we rely on are really three major data sources that we rely on. We have the burn severity mapping programs from the wildfire mapping programs, such as MTBS, Bear, and Ravage, and then LANDFIRE events that Brenda's talked about. And then our catch-all really is the spectral information from Landsat, in which we're using that to capture events or disturbances that are not captured in those other databases. And then we're also relying on a couple other data sets to help us with causality, and they're the protected area database and then a smart fire database as well. So just a little bit more about how this legend comes together and help you understand. At the top, the thing that we're the most confident in terms of severity and causality is that MTBS, Bear, and Ravage conglomeration data set. So that's our highest confidence, and that gets entered into that disturbance product pretty much straightforward with just a minor recode. And then the thing that we give the most confidence to in terms of causality would be our refresh events, and then also where we have our MICA detected change and severity information, and then so on down the line. As we know less about the source of the information, we're still fairly confident with its severity that we get assigned to it via this process, but we can only then guess as towards the causality. So a little bit of background about the LANDFIRE 2008 disturbance mapping efforts and why the switch. For LANDFIRE 2008, we used the vegetation change tracker algorithm, and really what that did was we're fed in stacks of imagery from 1984 to 2009, and then the vegetation change tracker algorithm calculates a forestness index and then looks for abrupt change in that index and then flags that pixel as being changed. And it works very effectively or fairly effectively in forested areas, but it doesn't work as well in non-forest and land cover types. So when it came time to develop a system for LANDFIRE 2010, we turned to our partners with the NLCD group to look and see because they're trying to crack the same nut, so to speak, solve the same problem. And they had developed a new tool, new index, called the Multi-Index Integrated Change Analysis, or MICA tool, which really combines multiple vegetation indexes and looks at that change. And then the hope is that it'll perform better across a wider range of land cover types. And those publications are listed there. So a little bit about how this disturbance mapping process works. I don't know how well you can see it on the screen or not, but the part I want to focus on now is the remote sensing aspect of that. So there's stacks of Landsat scenes from 2007 to 11, and a process through that MICA process that give us that change that's not associated with the other refresh events. So a little bit more about the stacks. Landsat TM imagery primarily, and then, as I mentioned, 10 scenes, a leaf on and leaf off, primarily TM imagery, and pretty sizable chunk of data. It's 430 some odd path rows for CONUS, so pretty sizable. Did rely on Landsat ETM a little bit to fill in some gaps where we just couldn't get a match, either because of clouds or phenology or whatnot. So, and then in terms of pre-processing, we relied on the LADAP's surface reflectance calculation. So the images are a 16-bit surface reflectance. And then we also used their system with the minor tweaks to identify clouds and cloud shadow and snow and ice and things like that. And then, of course, I'll go into the MICA system a little bit that we've leveraged from the NLCD group. All right, so once we get these images processed through that MICA system, then it comes into the hands of the analyst. So this is one of the most time-consuming parts of the process. And all the mapping is done on a path row by path row basis. So what we talk about, or this is the area of part of the process, called deemed the cleaning process. So we leverage a lot of different data sets, the digital elevation model, EVT, etc., to kind of clean out the false positives. Because one of the negative effects of the MICA process is it's very sensitive to detecting change, but it flags a lot of things that are not indeed change or change we're not interested in. And so the tricky part is cleaning out those things, of cloud and cloud shadow and things of that nature, cloud edge. And so for those cleaning process, we're relying on NLCD to give us those, identify those problem land cover types, the NAS cropland data layer, elevation model, things like that. And then we're also using a little bit of logic in addition to calculating the change between 7 and 8, etc., annual change. We're calculated change pairs between a skip year, for example, 7 and 9 or 8 to 10. So in this cleaning process, we oftentimes are using that logic to help identify some of those areas or knock out some of that false change. So, and then we're also using thresholds of the vegetation indexes that are calculated during this process as well. And then the analyst also has the option to add areas of interest of disturbances that just aren't picked up, things like grass fires and shrubland fires that sometimes, because of the timing of the imagery, for whatever reason, it's not picked up and flagged by the MICA process. So I hope you can see this, but I'll walk you through an example of kind of that cleaning process now. So one of the pre-image, or one of the scenes, this is one of the scenes in the stack. And then we have a same extent, just another scene from that year, so leaf off. And then we have a scene where we have a little bit of cloud shadow. And then last scene in the stack is cloud free. So this cleaning process, what the analyst has to do is try to, out of this area, separate out what's real change and what's not real change. So the shades of gray that you see on the screen, they're cloud and related. And then the reds are things that are flagged and change in both the leaf off and leaf on pairs. And then yellow and orange are just one of those pairs, respectively. And then, I don't know if you can see in the middle, but the fuchsia areas, and that area is one that is would be cloud in one pair and change in the other. So, as I mentioned before, the cleanup process, we use an Imagine model. Look at those data sets, and that's how this tool was developed to clean. And then the analyst is going to run this with a few different settings, and kind of an iterative process to hopefully knock out the things that are not real change and leave behind just things that we feel are confident that we want to map. So after this process and a little bit of magic, you're left with just the red pixels on the screen that are things that are mapped. Of course, that makes it look easy, but sometimes this can be a pretty frustrating process. So, okay, so a little bit, that is the cleaning part, and now I'll talk a little bit about how the refresh events and these other data sets are also contributed in and help us build this disturbance product. So the refresh events that Brenda spoke about earlier, they make their way into the final product, but we also buffer them by 500 meters to give us another level of information based on proximity. So we can, if we detect change, we can say, well, if MICA detects change, we can say, oh, well, it's outside of a refresh event, but it's nearby, so it may be associated with this. And we do the same thing with a SmartFire database. And so we'll talk a little bit more about how that comes together. So as I mentioned before, the MTBS bear ravage is, we just let that go right into the final product with just minor recoding, so as is. Same with the refresh events. Their spatial extent will get burned into the final product, and we'll add in severity information that we get from that mica process. And then, as I alluded to a little bit before, we look at proximity to other events based upon the refresh events and the proximity to the SmartFire points. And then, like I said, we inform possible causality from that pad data. So back to some more pictures. So leaf on, prior an event. We're going to see that, I don't know if you can see the dark area on the screen, but it's a probable fire. So we just step you through. Turns out we do have a lot of events submitted for this area. And you can see that, hopefully you can see there's the buffer information I'm talking about on these refresh events. And you see there's mechanical, I don't know if you can see on the screen, but there is some mechanical events as well, but primarily the fire. So as we go to assemble the final product, you'll see that actually MTBS and Bear Ravage, one of these programs, had mapped this fire, so that would take precedence and make its way into the final product. And you can see the highest severity areas would be mapped as red. So let's take a look now at the refresh events and how we use those a little bit. As Brenda talked about earlier, there's 21 types of events. 3 of those are associated with planning and things like that, but there's 18 disturbance types, and they're coded according to severity and persistence. So in this case, or with this assumption, then development is the most severe, and then followed by clear cut, and then on down, as you see on the screen, until the biological persistence or biological disturbance type. So I can walk you through how that data is there. So you have a pre-event image. Here you have an area that was disturbed. Turns out we have event information as well. So then, in this case, that project's this example is pretty straightforward. As it's assembled, we know what caused that disturbance because of the events, and then we have severity information from that. Standard deviation breaks on the DNVR. So. All right, I want to show you an example of how we leverage the SmartFire data to help provide causality to a disturbance. So if you're not familiar with SmartFire, the web address is listed there, but basically it's a unified database of fire-related information. That's my understanding. And the result is a point of where a probable fire was. So since we have a point information, we just buffered those points by 2,500 meters to say basically any disturbance that mica detects, we can say, well, if we don't have a true causality from another data set, we can say it's possible that this may be. So I'll show you an example of how that worked in reality. So we have a pre-fire image, post-fire image. I don't know if you can see, but it's kind of appears burned, at least on the screen, darkened or whatever, blackened area. So turns out, yeah, we have SmartFire data that occurred there. So then the final product would be coded something like that. It would say, we get a unique code that says, all we know about this disturbance is that we know its severity, and we know that there was a fire in that area, so we're going to say it's a possible fire-associated disturbance. All right, one more example, and I'll walk you through another example of how we use the pad data to do the same thing. So have a pre-disturbance image, and we have an area that looks like it's experienced some kind of harvest or cutting or something like that. So we don't have any other information. And now I'm jumping to the final product. I don't know if you can see on the screen, I hope you can, but yeah, these just disturbance polygons, these guys here have kind of a blue-gray unique code, and this has another unique code. And you might ask, well, why would that be? I mean, they're in the same area, they're the same shape, roughly the same size. Well, as we look at the ownership information, they're in a different ownership category, gap status, and so forth. Therefore, we're making an assumption that they're under different management. So this case might not have worked perfectly, but you get kind of an idea of what we're using. We're using the best information we have to try to make assumptions about what caused that disturbance. So. And then lastly, I'll just show you what happens when we have no information. So we have an area has been disturbed in the past. You may have noticed a change of additional disturbance in the center. And then we have really no other events or no fire occurred in that area. So We only know that it's an unknown disturbance, and we can assign severity on it based upon the DMBR, as I mentioned, from that MICA process. So anyway, that was a whirlwind tour, I realize, but it's a time-consuming process, and it involves a lot of computer time. There's over 4,000 scenes that were processed via the MICA process, and then on a mapping aspect, we're working through over 430 path rows just for CONUS. So, any questions?